Colloquium series. So today's speaker is Professor Pinaki Chaudhuri, IMSc Chennai. He is an alumnus of SAC College. His graduation is in the year 1997. MS from IISc Bangalore in 2000. PhD from IISc Bangalore in 2006. He has several postdoctoral experiences in JNCSR, LCVL University of Montpellier, France, LPMCA University of Cloud-Varna, Lyon, France, University of Düsseldorf, Germany, and then he joined IMSc, and now he is a professor of physics at IMSc Chennai. His research interest is soft condensed matter physics, glassy systems, jammed materials, non-equilibrium phenomena, etc. So today he will speak on exploring the world of disordered solids.
Thank you, Mr. Can you hear me? Yeah, so it's a great pleasure to be back in Raychaudhuri College. So I spent 3 very exciting years here, both here and outside. So it was a very interesting stay during these 3 years. Of course, I learned a lot, again, both here and outside. So I'm pretty sure all of you are also having some experience and will explore the world outside. Okay, so I'll be talking about work that I do or related stuff. And so what the title is Exploring Complexity and the World of Disordered Solids. So I'll explain what I mean by complexity and, of course, disordered solids. So before that, just a little advertisement about our institute, and of course you know that this is in Chennai. So these are the various themes in physics that we cover: astrophysics, fluid mechanics, quantum information, particle physics, quantum condensed matter, static, non-linear, complex systems, and of course. So there is a large diversity of topics that we cover at Math Science, and we are always looking out for bright students to come and work there. So as you know, we have both an integrated PhD program and a PhD program. So we always look forward to students from residency. So please join us there, and it would be great to do some nice research. So what I'll start off with is the Nobel Prize in Physics in 2021. So this was also a surprise to me because, firstly, the combination of people who had given the prize, and also the topic or the theme, the broad theme that was cited. So the people who had given the prize are Manabe, Hasselmann, and Parisi, and the work that was cited was for groundbreaking contribution to an understanding of complex systems. So Parisi is trained as a high energy physicist, but eventually, he has very similar contributions in high energy physics. But eventually, he moved over to static and has been one of the pillars of static over the last 30-40 years. Manabe and Hasselmann are not in physics per se, so they are more in applied physics field, working on climate, weather, and so on. So here you have very 2 disparate areas, and somebody working in condensed matter systems mechanics, and some set of people who are working in weather and climate and so on. And both these set of people are being given this prize for the contributions to understanding of complex systems. And specifically, if you look at the citation of Parisi, it says for the discovery of the entity of disorder and fluctuations in this resistance from atomic level and great states. So basically, here we notice the word disorder that I mentioned in the first slide, and I talk about why this is interesting. So then again, continuing the Nobel Prize citation, so it says, so all complex systems consist of many different parts, many different interacting parts. They have been studied by physicists for a couple of centuries and can be difficult to describe mathematically. They may have an enormous number of components or governed by chance. They could be chaotic, like the weather, where small deviations in initial values result in huge differences at the later stage. These years, laureates have all contributed to us gaining greater knowledge of such systems and their key word is this complex system consists of many different interacting parts. And in the next slide, we have examples, again from the, this I sourced from Wikipedia. So examples of complex systems: Earth's global climate, organisms, human brain, infrastructure such as power grid, transportation or communication systems, social and economic organizations like cities, an ecosystem, a living cell, and ultimately the entire universe. Okay. So these are very diverse examples of what would generally go under the rubric of what is called a complex system. Okay. So I know as when we start studying physics, we have only two fascinations: astrophysics or cosmology, and high energy physics came to. So there is a world in between, which is the world that we straddle and where all these complex systems live. And there is beautiful physics over there, which we may not be excited by at the very outset, because if you think about the unknown, I mean, the unknown is what is at the cosmic scale or what is at the very fundamental level. But there are things which are unknown also to us and the world that we see around us. Okay? We don't know how things function, how things work, or what leads to certain phenomena. And this is what we would like to understand also. So at the end of the day, physics is a science which is connected to experiments or observations. We are trying to understand what is happening in the world around us. It's not some abstract maths. If you want to do abstract maths, you do something else. But if you want to really want to understand the world around us, the materials, the phenomena, this is what our involvement in physics is all about. Okay? And this involvement, I'll come to length scales and time scales that we're talking about. So there is this entire world in between the fundamental forces and so on, and the cosmic scale of the galaxies and so on. That is this world which is, there can be several examples of complex systems starting from the minutest organism. So for example, how does a cell work? You may think this is biology, but more and more we know that this is an interdisciplinary science where physicists are contributing to a great extent to understand how a cell works, how many cells work to form a multicellular organism, how these multicellular organisms result in, mammals like us, and how we organize ourselves into societies and so on. So there is a hierarchy of structures that are there. Okay? And we would like to understand each of these levels using our training as physicists. Okay? So that is our perspective. Okay? So complex systems, just more in complex systems as systems, so behavior is intrinsically difficult to model due to dependencies. So since we have many interacting parts, I mean, just think of a society which have diverse human beings working together, living together, fighting, interacting, and so on. Similarly, you can take an ecosystem where you have diverse kind of species working, interacting together, and so on. A material where you have diverse components. So you can have a very complex material where you have diverse components which are interacting together. If you have multiple parts of a biological system, just a living, just a cell where it has many different components, okay, and different interactions that are happening. Not all that we understand, but the entire objective is to model. What is our objective as physicists is to model, to come up with simple models to try to understand this, whatever phenomena that is happening at different scales. So that is the objective. So we have many interacting components, and what we are trying to do is to come up with models to understand which are the relevant components which give rise to certain phenomena. Okay. Not all components may lead to a certain phenomenon, but maybe some relevant. Let's say you have million variables. It's possible. There are million variables, maybe 3 variables are relevant. So we have to find out those 3 relevant variables which give rise to the phenomena that we observe in the complex system. So complex systems, dependencies, constants, relationships, or other types of interactions in the past. So that's what I was saying with wide variety of interactions. Systems that are complex have distinct properties that arise from these relationships, such as non-linearity, emergence. So new phenomena can emerge because of these interactions, and so on, spontaneous order, counter-spontaneous order, feedback loops, so on and so forth. So the Nobel Prize citation also had this example from the work of Parisi, which may look like a very simple problem, but I'll try to explain why this is an interesting problem. So this is basically, I'll just read out. Every time many identical disks are squeezed together, a new irregular pattern this form despite them being squeezed in exactly the same way. What governs the result? So basically, they're saying Giorgio Parisi discovered a hidden structure in such complex disordered systems, blah blah blah. So what is the experiment that we're doing? We just have, let's say, some points in a box. Okay. And so I'll just draw you in that. So we have a box, and I have thrown some points inside the box. Okay. So all that I'm doing is I'm squeezing this box at some rate. Okay. It's a very simple experiment. So I'm squeezing this box at this rate. Eventually, my question is to ask is that where will this process stop? Okay. The process will stop. So imagine that you have this disc over here and you're squeezing it. The process will stop when you will feel a back reaction from whatever you're doing. So imagine that you have some carrot, or points of carrots, things, and then you're just pushing them. At some point, you will feel the rigidity of this kind of thing. Okay. So you will feel that it suddenly has become soft. There is a solid-like reaction. So what's the difference between a liquid and a solid? The only difference between a liquid and a solid is that a liquid, you can just put your hand through it. A solid, you will not be able to put your hand. You will feel the some resistance coming from that solid, right? So this is the rigidity of the material, unlike that of the liquid. Okay. So in this case, what will happen is there is a, so as you go on squeezing this together, there is a point at which, beyond which, you will feel a rigidity that is emerging. Now the question that we are asking is, what is that structure? This structure that we observe when the system has become, that you are feeling this rigid response. Okay. So what we observe is that, so imagine if you had infinite time to do this experiment, okay? And if you have this, all points of the same size, what will eventually happen is that you will have an ordered structure, what we call a crystal. Right? Crystal is an ordered structure. A crystalline solid has an ordered structure. So you know, this is from everyday experience, and this is you learn in. I don't think you will be learning within your understanding curriculum, but so basically, a liquid to solid transition is essentially a transition from a disorder to an ordered structure. So these are called phase transitions. So you see this in everyday life that if you take water, you put it into the freezer, it becomes ice. So it forms a solid, it forms a ordered structure. So if you did this experiment very slowly, okay, so eventually you will see an ordered structure in 2 dimensions because I'm doing this experiment. So I can also do this experiment in 3 dimensions. This is what people have done, and this is what you see in the markets, for example. You see fruits being organized in very organized lines by the owner in the market and so on. So you can have very ordered structure if you have infinite amount of time. But if you're doing this process very fast, that you're squeezing very fast, eventually what you will find is that you will get structures which don't have any order. Okay? So what we call disorder. So if you look at a snapshot, if I gave you a snapshot of this solid, of this structure, and a snapshot of the liquid at a slightly low density, because I'm changing the density, because I'm squeezing out the volume, you will not be able to make any difference visibly between the structure of the liquid and the structure of the solid. So a disordered solid has a structure almost same that of the liquid. Unlike a crystal, where you are going from a disordered liquid to an ordered liquid. So this is the difference. So you should ask me questions if you don't understand anything or if I'm going too fast. Please stop. Okay. So what these guys are saying is that, and the citation is saying is that, if I take the same initial condition, let's say, and I slightly change the way I'm squeezing it, the point at which the structure that will emerge, at which I feel this solid presence, will be very different depending upon the experiment that I'm doing. Okay? So even if I reach the same, the control parameter is not rho, the density, but something called vacuum fraction, which is total area of the discs by total volume. So this is the control parameter of the thing that we are doing. So even if I reach the same phi by doing this squeezing experiment, I will see a different structure if there is some alteration of the procedure that I am following. Okay. Maybe I'm doing slightly faster, slightly slower. Okay. Maybe my initial condition is slightly different. So basically, it's telling me that even if I reach this disordered solid, there can be many such realizations of the disordered solid that is possible starting from the same initial temperature with some small fluctuations. So this solid that we get over here, or this phenomenon that we observe, is called jamming. Of course, this word is very familiar to all of you. And we face road jams, traffic jams, and so on. And the word comes from there itself, jamming. So things are getting jammed, things are not moving, and therefore you have this solid-like responses. So we try to get some better handle or better understanding of why this is happening or how this is happening. So in 1998, these two scientists from Chicago, at the time in Chicago, Amal and Raychaudhuri, they came up with this phase diagram. So here I have three different axes: temperature, density, and rho. Okay. So this experiment that I am doing over here is an experiment along the density or inverse density. Okay. I am reaching this gap state inside. So what this claim is that, irrespective of the path that I take, whether I am lowering the temperature in some circumstances, decreasing the load in some circumstances, I am always reaching this disordered state, disordered solid state or a jam state. Okay. Now the question that one can ask is the following: are all these disordered states having similar properties, or this disorder of the jam solid having similar properties? As I am approaching this jam structure, do I see similar phenomena? Right? So independent of whichever path I take, are we seeing similar phenomena? Are the observations very similar? So these are the questions that, as you can see here, there could be physicists who are working only on the thermal route, just cooling systems. Okay? So they can now start asking these questions that the phenomena that people observe while they are packing or doing this packing problem is very, the phenomena that we observe over here is very similar to the phenomena that we observe when you're cooling the system. Yeah.
Sir, how disordered solids is different from liquid crystals?
Liquid crystals is completely different. Liquid crystals have a completely different. Liquid crystals are so how do liquid crystals form? Liquid crystals are, for example, you meet some anisotropic particles like rods, ellipsoids, and so on. Okay. So there you could both have a crystalline structure and liquid-like structure. So maybe we can discuss this at the end. So you could have, let's say, it's a three-dimensional system. In one direction, you could have, or let's say there is some order in the z direction, but in the xy plane it can be completely disordered. Okay, so that is like liquid crystal. There's one transition of between these liquid crystals happening. But this we are talking about really point-like objects or circular objects. Let's say to make life very, very simple, circular objects, maybe completely all of the same size. Okay, maybe slightly different size, which is useful sometimes. And these are forming this jammed or disordered solids and so on. So then, so this phase diagram or this schematic diagram, this is just a thought. Nobody has proven it at this point, 1998. So this is just a thought, and so let's say last 20 years or so, people have been trying to figure out whether this thought is correct, whether there are phenomena which are similar across these different paths and so on and so on. So now this connects to some problem that people have been studying for more than a century, what is called the physics of glasses or glass transition. So there are glasses, in our daily life we see glasses of different kinds, and it could be some metallic system, it could be soft materials which we use, food, cosmetics, chocolate. It can be something like snow, tar. So it can be various kinds. So this kind of solids. This solid we use, toothpaste, is a soft solid. Okay, it's a disordered solid. Okay. So why do we call a toothpaste a solid? We are squeezing it out. It is flowing almost like a liquid. But when it is on the toothbrush, it retains the shape that it had come out with. Okay, that's important. It is retaining the shape. It's not melting away. If you imagine you pour honey on the toothbrush, of course it will flow away. So the distinction is there. The solid will always retain its shape unless you do something else to it. Okay? So you take a little bit of jam, you put on your bread. Unless you use that knife or whatever you want to spread it with, it's not going to spread. It will just remain like a dollop of the jam. Because it's a soft solid. Okay. So there are wide variety of yogurt, soft solid. Shampoo is also a soft solid. So there are hundreds of things that we see in our daily lives which are these soft solids. All of these are dissolved. So you can see that, I mean, crystals of course have their own place, but there are huge variety of materials in our applications in our daily lives which are these soft solids. And not just happening on mountains, snows, which is like a soft solid, I mean, it's like a dissolved solid which is flowing and so on. Okay. Landslides happening, soil which is flowing. Again, it's almost like a rigid solid until that landslide happens and it starts flowing and so on. Okay. So now coming to landscapes. So landscapes, we are, I mean, these solids straddling from 0.1 nanometer to 1 centimeter. So they come from the constituents. Okay. So for example, in the metallic classes, we have atoms, which are, this copper, zirconium, these are the atoms which are forming the metallic class. Polymer classes, certainly some polymeric systems which are forming this kind of polymer classes. We have colloidal classes which are like micron size particles 10 to the power -6. So we go from 10 to the power -10 to 10 to the power -6. Then foams are slightly, bubbles, you can see Gillette foam, soft solid. So these are foams, soap bubbles, you can make a conglomeration of soap bubbles, these are soft solid, these are bigger things. And then of course granular solids like pilot grains and so on and so forth. Okay. So now the other interesting thing is that some of the solids are what we call thermal, some solids are athermal. What is the difference? Thermal is when the material can feel the presence of temperature. You know about Brownian motion, right? So you put some dust particles in water, that will form a Brownian motion. So this is a random ball that is forming because it is being kicked around by temperature, the thermal fluctuations and so on. But if you take a grain, a big grain like sand or something like that, you put it in water, it will sediment. Okay? In principle, you could choose a solvent which will balance out the forces and it can remain dispersed, will not sediment. That is possible. There are solvents which can do the balancing of forces. But their temperature is an irrelevant variable. The constant particle is so large, the thermal fluctuations don't affect it at all. So granular solids are examples like that. These are solids which we call athermal systems. Okay. On the other hand, we have all these thermal systems which are much smaller where thermal fluctuations are important. But irrespective of whether it is thermal or athermal, the physics or the responses that we observe are very similar. Okay. So this is this entire world of dissolved solids that we talk about. So as I said at the beginning, what we would like to understand is the formation of how these solids form and how these solids respond. Okay. So if I hit some solid like this, how does it respond? What are we trying to do? We are trying to understand what is happening at the very smallest scale that lead to phenomena that we observe. Okay, that is our objective. So we are trying. So what is the difference between thermodynamics and statistical mechanics? Thermodynamics is whatever the macroscopic phenomena that we observe. We have written down the laws and so on. But statistical mechanics, we are trying to understand on a very microscopic degrees of freedom how this large scale phenomena, this macroscopic behavior of the thermal behavior that we observe. Exactly the same thing. We want to model systems at a very small scale and then build up from there and try to observe the phenomena that we see. So and then the important thing is there is a need for numerical modeling. Okay, there is a very small set of systems or set of problems in the world where I can write down exact equations, or I can write down the equations in integer maybe, but I can solve those equations. So then we have to take recourse for the numerical methods or numerical techniques to solve or to. For example, some of these are very simple. So you have Newton's equations of motion, let's say, but you have million particles. So you integrate now because million particles, the equations of motion of the million particles. That is not a big task, and a computer can do this. But the interesting part is that once you integrate the equations of motion, so you see the time evolution of the system, now you have to do your measurements. Measurement is the important part. Do your measurements at any instant of time between 2 time points and so on, and then try to understand what are the phenomena that you are observing. Okay, so the interesting thing about these glassy systems is that what you observe is that if I measure the viscosity, this experiments will do viscosity as a function of inverse temperature, then what is observed in this glassy systems is that there is a very rapid increase in the viscosity as you go to lower and lower temperatures. Okay, the systems become very viscous. So you take the tar that they're pouring on the road. This is an experiment where in New Zealand it is happening in the town of Canterbury. The tar has been flowing since 1927. And the ninth drop fell in 2014. So you can imagine how slowly it is falling. Okay? So this is how viscous it is. The person who was doing the experiment passed away recently, and it has now been handed over to the next person. Okay? So maybe in next 2030, the next drop will be. So this is how, so there is high viscous, almost like solid like response and so on. So if I mean, just to go back to the stories. So this one, what is happening over here? So you are shaping, I mean this is, I don't know whether the glass blower is there or not, but in principle everywhere there was a glass blower who was making these shapes and so on. And I mean then you of course you have things that you have in your living room, vases and things like that that have been shaped by glasses and so on. Okay? So this is basically molten glass which is being shaped into designs and so on. Okay? So of course glass is solid. I mean the base is solid. So it is slightly heated such that it has this finite viscosity so that it can flow, that you can make shapes out of it. And then it is coming in contact with the room temperature, okay, and it is freezing. So therefore you are getting this very intricate shapes that are here. So it's very borderline case between the point at which has a finite viscosity it is flowing and to the point where it is not flowing visibly. I mean there was a folklore at some point that if you go to old churches, you will see windows which are slightly thicker at the bottom, which is not true actually. People used to say that the glass is flowing since centuries. It's not true. But that was the folklore that was there. Okay.
Due to the relaxation time is very high.
Yeah, the relaxation time is very high, yes. So the physics that we're trying to do is, where is the challenge? The challenge is what we call multi-scales. So we are trying to model from the very microscopic phenomena or the microscopic degrees of freedom to the phenomena that we're observing in millimeter scales and so on. Okay? So basically what we have to do is to build macro scale descriptions from microscopic phenomena. So this is the objective. So for example, if you talk to people working on glaciers and so on. Okay, so they are measuring how the glacier moves. Okay, so they are also doing some modeling, which is modeling at that scale. So those are all empirical laws. Okay, so they are saying, okay, the glacier moves at this rate, so therefore there is this force that we are acting, and therefore I can write down some empirical law. But how do we understand an empirical law from the properties of the ice? That is a very difficult question. So we have to go from that, basically building up from the ice crystal or whatever, ice, glass, whatever you call it at a very small scale, to the glacial scales. That is not happening very soon. I mean, because there are various bridges that need to be crossed. So basically from that nanometric scale, you have to go to the next scale and see whether you have, when you have integrated over some degrees of freedom or something, some scales, whether whatever you have, whatever theory you have constructed is matching with whatever observation you are making at that scale. So you have to go from one scale to another. So this therefore is a multi-scale problem. And therefore we need large-scale computing. Unfortunately, whatever I have seen in India so far, the passion for computing is very little. Okay? I mean, whatever be the reason, maybe because we are not exposed to that degree of computing at the undergrad scale, at schools and so on. Okay? But the passion for computing that India requires, only now we have a national supercomputing vision. So there is a vision to have huge computing facilities where we can do large-scale problems. Because there are physics that we can't do at using a desktop. Okay, so if I just give you a desktop, you can only do physics up to a certain time, scale, and so on. So what we would like to do, so for example, I mean, people who are modeling the weather, for example, they need huge computers, I mean, huge this kind of facility and so on, to give you predictions over certain length scale, let's say kilometers, over certain time scale, let's say years. So you have this worldwide models. I mean, if you go to, there are many free software now in the market. So for example, you have software, I don't know whether you follow, there is this website called Windy. It gives you weather patterns, climate patterns, things like that over certain scales. So if you go very close by, you will see that there is some resolution below which these predictions are not there because they are coarse grading or there is a grid over which they are doing the numerical computing. So below a certain resolution, like a few kilometers or so, they cannot give you the information. Okay. So the more resolution that you want to add to the problem, the more computing power you need. Okay. So suppose I want to give you what is happening in College Street next 7 days. Nobody will be able to do it. Maybe it's not necessary, not needed, but if I wanted to, I couldn't give you because I don't have the computing power to have that kind of resolution. Because I'm trying to model some phenomena which is happening. So again, if you again use wind, if you have to really zoom out to see the cloud patterns, why are we saying that something that's happening in China is affecting India? For example, let's say, because the winds are coming from there, over the mountains and so on. If you look at cloud patterns, you will see how large scale this hydrodynamic phenomena are. Okay. So to model that, we need large scale computing. Similarly, also in material modeling, we need large scale computing. Why do we need? Because we need to model, as I say, large time scales, large length scales. We need, so you are evolving the system. If you want to resolve your phenomena over certain time windows, you need large amount of data. You need the ability to handle large amount of data. We need storage. Okay. Again, we are not, for example, as physicists. Let's say, what's the distinction between a material scientist and a physicist? A physicist will always try to solve the simplest problem first. Okay. I will try to solve, let's say, with disks, simple hard disks, or simple what we call Isaac models and so on, a phenomenon with some more complicated phenomena. We may fail, but we will try the simplest model first. The material scientists will take Hopper's Zirconium model and try to solve that problem. Okay, so that is where let's say the distinction. We are trying to do simple models. But even if we do the simple models, we need large scale models to which we need to observe over large time scales and large length scales in order to get any predictions over large scale phenomena. So what we are asking is, if I go from microscopic to macroscopic scales, what are the emergent behavior? So and why is computing very helpful? Because there are also our theory colleagues who are making various theoretical predictions. Okay. So for example, this is gravitational waves. Some people observe, let's say the observers observe some signal. But how do you know which event is happening? You don't know. Only because you have a huge database of numerical simulations which have carried out simulations and seen what are the possible signals that you will get if this event happens, then only you can go back and match my signal and say, oh, this event is there in my library, possibly these two black holes have merged or whatever, collided, and therefore I am getting this. Because I have done this, somebody is doing the simulations. If those simulations were not there, I wouldn't be able to make any sense about this signal mechanics. So to test theoretical ideas, we need to do, and the thing is, in experiments, you can't do all experiments. There also, you have finite resources or finite possibilities. Okay. You just can't say, okay, let me tweak something over there, maybe I add 100 grams of this, 200 grams of that. That's not possible. You have finite resources. So computer simulations allow you to do, thought experiments of diverse kinds. Okay, just like Einstein's thought experiments. You are doing thought experiments, you tweak something there, you tweak something there, you perturb something there, you look at what's happening, and then maybe something reasonably interesting comes out, then you can tell your theories, go and try to understand this, go and tell the experimentalist, maybe you can try to observe this and so on. That's how things work, okay? Unless somebody makes an observation or prediction, maybe a theorist makes a prediction, then I'll go and do the numerical modeling and see if it's correct or not. Maybe I do an observation and the experimentalist or the theorist try to see whether it's realistic or whether the theory supports that idea. Okay, so that's how things work. Of course, then exploring phenomena, for example, freezing of simple spheres. Okay, if I give you a system which is just spheres, there's some solvent. Okay, some hard spheres. The first people who observed this freezing were actually people who were doing computer simulations. And people who were doing theory didn't believe it. Actually, if you go back and see, in APS, American Physical Society, there was a vote taken whether that phenomenon that was observed is correct or not. Because nobody believed it. Okay? Eventually it turned out to be correct. But if you go back to those early, when they proposed, thought, okay, we have done the simulations, we find this observation, look, it is freezing. Why what is a surprise? Because if I take hot sphere system, there is no, so if I look at the free energy has two parts. There is internal energy, or what we call interactions, and the other part is entropy. For hard spheres, if they are not in contact, the energy is zero. Okay? The only contribution is from the free energy is coming from the entropy. Okay? So, and the freezing that they were observing, if at all it was happening, is completely due to the energy. And there was no theory at that point of time which explained freezing due to energy. Eventually it came because this observation happened. So, new phenomena we can observe, and then the theories can work out, or you can work together to figure out why this is happening. And of course, then design new materials. You can put things together and we can see, for example, maybe I come to this again later, how to design new materials and so on. Okay. So then what is the property of this disordered systems? So if I look at the energy of the system, suppose I have n particles, okay, in 3 dimensions. Okay. So then total they have 3n degrees of freedom. Okay. So this energy function over here, so it is residing in this 3n dimensional space. Okay. So I have this space which is spanned by the vectors R1, R2 to Rn. So this is this energy function which is residing in this high dimensional space. I can also write a free energy function. Let's forget that for a moment. So the property of this system, this disordered systems, is that this energy landscape is very rough. It's almost like mountains. Okay. So there are multiple local minima inside this local landscape. Okay. So this is a schematic picture that I have this very rough landscape. Maybe there is an angle, I thought to tell you what is an angle glass. Maybe there is a crystal. Maybe there is a structure which is completely ordered. There is a local one energy minimum in this five-dimensional landscape which corresponds to a crystal. Maybe it is not there, we don't know. This is just a picture. Okay. And if there is a possibility of a liquid to glass phase transition, maybe there is also an ideal glass minimum. We don't know. Okay. So these are all thoughts, hypotheses that we need to test out. This is what we are doing. Okay. So how do we understand this dynamics or this viscosity increase as we go to lower and lower temperatures? The understanding is the following, that because if you imagine that if you have to go from one peak in the mountain to another peak in the mountain, or one valley to another valley, it might take a huge amount of time because you just have to go up, down, and so on. Okay, so when you have lowered the temperature of the system in this high-dimensional landscape, okay, so you have many troughs and valleys and so on, hills and so on. So you will just go into the bottom of one valley, come up, go down, up, and this takes enormous amount of time scale. Therefore, this relaxation time is very large. Therefore, this viscosity is very large. Okay. So this rough landscape is what the property of these disordered systems or the disordered solids and so on. And this is where the complexity comes in. So then I can ask the following question, that I have this so I have a landscape which is very rough. Okay. So then can I suppose I take one system over here, one system which is residing in this minimum, another system which is residing in this minimum, okay, and some system which is residing in this minimum. Do they look similar, different? Okay. This is one relevant question to ask, right? So what Parisi showed is that if I look at, so what I can do is I can compute something called overlap. Overlap is very simple. I put a system on top of another system, okay, and see how similar or dissimilar they are. Okay. So what Parisi showed is that basically if I take this overlap measurement, okay, then I'll observe typically that there are some systems with which I have overlap to 0, and another set of systems which have an overlap to 1. Okay.
So with what? Overlap with respect to?
Well, let's say I'm doing overlap with respect to this. So I have a reference state and I'm doing overlap with respect to this reference state. So basically then what I observed, or what he predicted, was that there is what is called vertical symmetry. Let's forget what is that. So below a critical temperature, this vertical symmetry happens, and this is what Parisi is famous for, and this is what is part of the Nobel Prizes. Okay. So basically, there is a landscape has a certain structure. Okay. So with some local minima in this energy landscape, there is more overlap, okay, which is this Q1, and then compared to other minima which has less overlap. Q0. So this is what we call a one-step symmetry vector. But what is also predicted is that you can have multiple such symmetry gradients. So if I now zoom down into one plane, now you have another rough structure over there. Okay, so there can be a hierarchy of structures that are emerging inside. So essentially, my landscape, so I came from here, I went down, and if I go, it forks further and so on. So it's almost like a fractal-like structure that is emerging at the end. So these are the pictures that people have drawn. So these are predictions. In some example cases, we have seen that this is possible. So this was some static picture of the landscape. Okay, so firstly, this was a hypothesis. So let's say over 20 years, people tried using different systems, models, and so on to actually show that this is true. Okay, you can never be confident because you always have to. In statistical, if you're doing statistical mechanics, you always have to do larger and larger systems that until you have convergence of results. Okay, so let's say this, we have now proven that this is true. Now we would like to know, and this is something we have done recently, where we would like to know spatially how different they are. Okay, so if I put this system and this system, for example, let's say. So what are the structures that are emerging? So this is basically, if I move from here to here, how much of displacement each particles will undergo? Okay. So these are just displacement vectors. Okay. For a very large system. So it has a certain. So basically, what it is telling me is that there is very small displacement happening over here, but there is something interesting that is happening over here. Okay. So basically, some reorganization. So most reorganization that is happening to go from one minimum to another minimum. So it is happening around here, and rest of there it is very little. So that is what we call a local event that is happening. One single event that is happening that takes the system from here to the local system. Okay. And if I went somewhere far away, I will be having many such events. Okay. So suppose I want to go from here to here, let's say, there will be many such events that will be happening. So these are things that we are trying to understand. What is the structure of the landscape? How many paths are there between different local minima? So that will give us the topography. So far we didn't have the topography. Now we are trying to understand the topography of this landscape. And when we talk about complexity, complexity is essentially the size of this. How many minima are there? Okay. So typically you have exponentially n number of minima. Okay. So easily, if you think about, let's say, 1,000 particle system, you have this number of local minima that is there. So we would like to chart out this landscape just as some explorer charts out the mountains. We would also chart out this landscape in this kind of systems, and this is what we are able to do now because we have the computing power.
So your black regions are the local minimum?
No, black regions are the ones which are the flips that are happening, or structural rearrangements that are happening that is taking me from one minimum to another minimum. So this is large displacement, this is small displacement. So there are large, basically if you zoom in, there are large arrows over here, and these are very small arrows. So most of the reorganization that is happening to take you from here to there is happening over here. And it has this nice quadrupolar structure. That is also interesting. So it is not isotropic, it has this quadrupolar structure. So I will not go into the details of the quadrupolar structure, but I will come back and I will show you some more pictures. Okay, so how much time do I have?
15 minutes. Pinaki, one thing.
Yeah.
So I think the overlap, what are you talking about? This overlap is just contrary to the Hamming distance.
It's different metric. Hamming distance is one metric, overlap is another metric.
So suppose you are dividing this lattice by 1, 0 only. So Hamming distance will give you how much different it is.
Yeah, exactly. And these are showing you how similar they are.
How similar.
Yes. But yeah, complementary you can say. So this is another metric here where we are having the spatial structure of the distance. So rather than some absolute number, so here we are giving you the spatial structure of the distance.
Sorry, what is the difference between these two plots?
This is, let's say, too close by minimum, this is too far away minimum. So actually, this is very interesting. So what we have done is very simple. We have taken some state, okay? Let's say this is some high temperature state. And we have done, what we have done is just done different minimization algorithms. Okay. And, well, I haven't talked about minimization again. We have done different minimization algorithms. Depending on the algorithm, you land up in different minimum. Okay. So you can look at the numbers that you're getting in energy. Okay. Maybe you have two energy levels which are very close by. Now, if I compute the distance between that and spatial form, I'll get this. If I look at two levels which are slightly far apart, so I'll get this kind of thing. Okay. The same initial condition, different algorithms just gave us this different energy levels. Because algorithms are as good as, some algorithms allow you to cross some barriers, some algorithms don't allow you to cross some barriers. So in some cases you can move very low energy states, some cases you can't move this way. Okay, so the next thing that I would like to show is something that is sort of my main bread and butter. So what happens now if I take one of these energy states, this minima that I get. Okay, so suppose I am able to, since I came to my minimization difficulty, I'll tell you also about this. So all this is some nice picture that we have, that the landscape which has many of its local minima and so on. Okay, but the question is, if I, for a model system, let's pick up a model system, I want to construct this landscape. Okay? So what I do is I do exactly what I told just now. I take some finite high temperature state and I'll try to minimize the energy. Because that's how I'll go to this energy minima in the landscape. Okay. So my obtaining the minima is as good as the algorithm that I use. Some algorithms are good, some algorithms are bad. So far, what we have been sort of being able to prove are only energy levels which are higher up in the landscape. Only now we have better algorithms which allow us to go to lower energy levels. Okay. Again, funnily enough, this algorithm comes from Dr. Parisi, who got the Nobel Prize. Okay. So, there is this picture that Nobel Prize winners are either pure experimentalists or pure theorists. This is not true. Many of them are stalwarts in computer simulations. Actually, Parisi, even in high-energy physics, he has contributions in numerical techniques. So, if I had to bring an online message today, do numerical simulations, do computation, and there is a lot of things to do. Okay. What I tell you is about now if I take this low energy state or some energy levels or state systems deciding this energy minimum and try to apply both. Okay, so imagine you have a magnetic system which you are familiar with. I'm just using the language. You have a magnetic system and then you are applying a magnetic field. Similarly, I have taken my system which is residing in the energy minimum and I'm applying an external field, which is as the system that I choose, the field will be accordingly. Okay? So the interesting feature of this kind of systems is the following, that again, going back to the examples that I used earlier. So for example, if I take toothpaste, it is sitting there on the toothbrush unless you do something to it. Okay, so if you tap it, nothing will happen. You have to force it. There is a critical force that you have to use in order for the toothpaste to flow or whatever. You have to brush. There is some force you're using. You are squeezing the thing to come out of the bottle. There is a force, the stress threshold that you have to apply. So basically, these are called P-stress materials. So basically, what you need is a finite stress for the system to start flowing. So this is basically the amount of stress that you have to apply and the flow rate that will emerge. Okay. So you can not use enough. Okay. So alternatively, so this is basically as a what we call steady state. So basically, imagine like it's a non-equilibrium system. We are measuring something in a steady state. So in an equilibrium system, this would be something like equilibrium equilibrium. So then there is other thing that we can observe is how the system is loading as a function of time. So elasticity, this is something that is familiar from undergraduate and so on. So this is the initial part, it will be a Homogeneous solid, it will be elastic, it will be a linear response, and then it will become non-linear, and then it will break, and then in some cases it will flow. So if it is a metallic system or shock, it will break. So it will be a fracture. Okay. But if it is something like viscous, highly viscous, it will start flowing. So existence of the yield straight and yield straight. So now imagine, if I go back to the landscape, what is happening to the landscape as I do the loading. So this is my landscape, the system is sitting over here. I start doing the loading, the landscape becomes unstable. Okay? So it starts tilting. And as it tilts, beyond the critical tilt, the local minimum becomes completely unstable and starts going down. This is exactly what is happening. And as the system goes downhill, what is the event that we see? Is exactly the event that I showed you earlier. This quadrupolar structure, this displacement field that I showed you earlier. So exactly as I do the loading of the system, the event that shows up to go from one minimum to another minimum in this kind of events that we constructed out as distances and so on. So these are the elementary events that take the system from one local minimum to another local minimum. So these are elementary events, and these are much complex structures that we see later on. We have systems which are flowing much more in one part of the system relative to the other system. These are called shear bands. So these are reliefs that you observe in some metallic systems, for example, this kind of wet. So these are slip lines that systems has deformed more. So these are called shear bands and so on. So then also what you can observe are what are called avalanches. So suddenly what you will observe is, these are things that you see in real life also. You take a granular pipe, you hit it somewhere, there is suddenly some avalanche that will happen. Here also we observe cascades that many such, so what is happening is I'm tilting the system, suddenly it topples so it goes very far away from where it was. So there is a cascade that is happening. So many such events have fallen in line with each other and these cascades happen. Okay. So these are all observed in numerical situations. The other thing what we can do is, for example, again, I can take systems from different energy levels, 1, 2, 3, and I apply the same load. Okay, same amount of stress I apply. So in some cases, the system will yield, that will flow like this. In some cases, it will remain static. So basically, what it is telling me is that I need to apply much more stress for the low energy levels for the system to go into a flowing state. Then there will be these two levels. So there is what we call history dependent, or there is memory of the initial state that has to be raised before you can go into some state. This movie will not miss. This movie, unfortunately, this is a beautiful movie. So now we are also trying to understand validated systems, as I said earlier on. So this is actually the movie you can go and watch on YouTube. So this is the movie of a growing of a wing. Okay, Drosophila, the wing is growing, developing. Okay, from the infancy stage to eventually the wing formation. Okay. So what we observe are cellular flows. So basically how the cells are moving and so on. Okay, if I zoom in and play you this movie, and this is the movie of some foams. Okay, and I'm squeezing it. So if I zoom in over here and I show you this movie, you will not be able to make any distinction. Okay. Basically saying that whatever is happening in the biological systems at the global cellular state is very similar to this kind of disordered solids that I observe. A completely mechanical system to a biological system where there is life inside it. So since the system is disordered and you have behavior which are almost glassy and so on, you observe things which are very similar to the mechanical system. Actually, there are a lot of movies here, maybe I will not go into it. Okay, so there are these ideas now. So what I'm now working on are what are called active classes. Active classes are basically trying to model this biological cells or the assembly of cells as this kind of disordered solids, and then looking at the properties of these disordered solids and looking at what's happening in the biological systems and so on. So the simplest example of an active solid is basically that again, if I have this collection of discs, and imagine that because of some chemical reaction that is happening inside, it moves in one particular direction. So if it was always moving in one particular direction, that would be what we would call a persistent walker. Persistence. So in some cases it can be completely persistent, in some cases it can topple, move so they can have this kind of non-persistent walk and so on. Okay. And then one can observe some very interesting phenomena which unfortunately the movies are not playing. So you can have some spirals, you can have intermittency and so on. And this is actually worked by Raychaudhuri, who is also a former student of residency. And we have been working together. So to summarize, what basically I try to tell you is that there is some very interesting complexity that is there in solid solids, which exist in different forms. There is an underlying rugged energy landscape, hierarchy of local minimum. There is a history-dependent response, and we need to understand the systems. And to understand the systems, we need very good methods of computational prowess. And eventually, we need to develop what are called multi-scale models and so on. So it's also some work where people do some modeling at a slightly higher density, and then we try to see whether the microscopic scales bridge with those scales and so on. So this is also work that we do. I'll stop here and then I'll take any questions. Thank you.
If you have any question, you may ask.
Yes.
You are the Hamiltonian.
Yes.
What is the dynamical law?
So,
Here you are using.
So if I just want to study plasma machine, finite temperature plasma machine, Newton's equation. Only if when I'm applying the drive, in some cases these are non-Hamiltonian. I mean the drive you cannot in some cases you can incorporate into the Hamiltonian, in some cases you cannot incorporate into it. If I'm doing a study the non-equilibrium version of this system, so when I'm driving the system, then the drive will not be inside the Hamiltonian.
External drive, driven system.
Yeah. Suppose I'm deforming the box or something like that. Yes.
So you have said that Drosophila wings in the last part, but those are active matters.
Yes.
And the foam is not active matter.
That's what I'm saying. That in one case I have what we call passive system.
Yes.
And the other case we have an active system. But if you look at the flows that are happening, if you go close, if you look at long small length scales and look at flows that are happening, if you forget that this was a Drosophila and this is a foam, you will see exactly the same. Okay. Because what is happening? It's a disordered solid here, it's a disordered solid here. Some drive is happening, some drive is happening. In one case the drive is macroscopic in the case of the foam, in the other case the drive is local. But what we can show is that the events, the local events that are happening, the elementary events that are happening are exactly the same. Because it's a disordered solid which is being driven. That's it.
Another question?
Yep.
In the slide, you have told about the transition between the crystal and the ideal class.
The ideal class, yes.
What is the ideal class?
Ideal class, so, okay. We don't know whether an ideal class is there or not. So all that we are observing is the following, that my relaxation time speed, this is increasing rapidly as I'm going to lower and lower temperatures. Why is this happening? This is the question. Do you mean like? So this is all that we are observing. The relaxation time is increasing rapidly as I go to lower temperatures. Okay. So this is what we call the, let's say, slowing down, dynamical slowing down. So this we know from physics of phase transitions, that whenever I am approaching a phase transition, there is a slowing down of the dynamics. Let's give a concrete example. Suppose I have, I don't know how many of you are familiar with Ising systems or spin models. So basically, what you have, so there are systems, let's say you just have this up-down symmetry and so on. And all these kind of systems which have this kind of states. So as you're lowering the temperature, you can either go to a system which are all up or down. Okay, so these are the only two possible down states. So when I'm approaching this low temperature state, there will be regions which have, let's say, all up, and there will be regions which have all down, and so on. Okay. So there are these huge chunks of domains as we call. These domains have to flip in order for this order to get. Okay. And if I have to flip such a large domain, okay, it takes enormous amount of energy and therefore a lot of time. Okay. So that is how this is going down in the dynamics. So if in the class what I am observing is that relaxation time state is increasing as I go to lower and lower temperature. So my hypothesis is that there is possibly a phase transition that is happening. So the question is, what phase am I going to? Okay. So in the case of the liquid to solid transition, I know that I am going from a liquid which is completely disordered to a crystal which has this translation and rotational order. So maybe I am now, the phase transition that is happening between a liquid and a glass, okay, an ideal glass, which has some kind of order. What we call something like the order parameter, which tells us the degree of order that is there or the kind of order that is there. Unfortunately for the ideal glass, we don't know what is the order parameter. That is what the entire mystery of the glass condition is, that we don't know what is the order parameter. Maybe there is this ideal glass, and this is not what we are seeking, that is there some order that is increasing. What order I don't know. That is what today I'll come up and say, okay, you take 5 particles, maybe they are organized in this way, and you look for this kind of pattern. So people will go in search of that pattern. Maybe this hypothesis is wrong. Maybe there is some pattern that we have to find. But if that pattern is found and a repetition of this pattern over large space, that is the order that is there in the ideal class. Okay. That may be there, may not be there, we don't know. But that is a hypothesis.
Any other question?
So in the locality, now when you are going from one to other, so you are like using some simulating analytics or something.
Yeah, you can use those. I mean, you can.
Your simulation model.
What we did here, I gave you the picture of that. But basically, what we started off was I start from a high temperature state and I'm just going downhill. I'm using different algorithms and then I take these 2 states and then I just find the difference.
You told about that highly viscous fluid.
Yeah.
Whose 9th drop was in 2014.
Yes.
So, any effect of weather change on it?
So these are what are called athermal systems. So temperature doesn't play in this. In most cases, or you are in ambient conditions like where the temperature has that role always the same. So it doesn't. Temperature doesn't matter. So for example, road traffic. Of course, if it's high temperature and the sun is there, then it might melt. But the surface might melt slightly. But below, nothing will happen. There will be my surface effects, but the bulk will be different.
There is a slide, A and B figure.
Yeah.
One local minimum for another.
Yeah.
Can you just differentiate the figure? A and B difference?
Yeah, so what I'm saying is the following that let's say first I say there is this rough landscape. Okay. So there is one minimum over here, another minimum over here, and so on, and another minimum here and here. So all that I'm asking is, suppose let's say I take this state, then I can ask what is the how different is this state from this state and this state from this state, for example. So what the simplest thing that I can do is I can find, so I can do 2 different kinds, I can give you 2 different kinds of things. I can give you an overall number, okay, some distance, that's what with the saying, I'm having distance, for example. So for example, I can put one copy on, I can put this copy on top of another copy, and just 0, 1, 0, 1, 0, 1, I can tell you how many ones are there, how many are there, what is the match of this match. So that is the overall number I can give you. Alternatively, I can give you a picture at a microscopic scale. Okay? How much each particle needs to be displaced in order to go from one minimum to another minimum. Okay, so I can draw a vector in this 2D space. That will take me, for each particle I can draw a vector, and I'm just plotting, this is just a vector map. So what you are seeing is that some of the vectors are set very small, some vectors are very big. and there is some nice structure that is emerging, this quadrupolar structure. So in this case, it just took one flip, what we call shear transformation. This is called a shear transformation zone. So this is one zone, transformation zone that is happening, and there are many such SCCs over here. So basically what it is telling us that in this case the two medium are very close by, just one flip away. I mean, just think of a spin flip. Okay, so one spin flip away, and in this case it's very such many.
Any other question?
Yep.
I have a question. You said that the order parameter that's there for Bassi systems is not actually known. So how do we determine the transition temperatures for
We can't, right? So what we can do, so how does an experimentalist tell you that there is glass transition happening? Because you cannot have a glass transition where an experimental has no handle on your order parameter. I mean, even in the case of liquid to solid, it's looking at melting or freezing and so on. So in the glass transition theory, that is sort of like a understanding that experimentalists have, that if the viscosity is taken to the power of 12 twice, then I declare it's a glass. So that is the experimental convention. Okay? So whether it makes sense or not, we will see later. I will get it with the later, but this is now to make sense. Okay. So now when I'm doing alternatively, what can I do? So I have my data for time scale as a function of temperature. Okay. I can try to fit this with a diverging function. So the simplest thing I can try is 1 by d, for example. Okay. Summation. So then this would mean that the divergence, I mean the point of divergence is equal to 0. So I will see whether it fits or not. If it doesn't fit, I discard. Then I try something else. Okay. So if my data fits this, all I'm doing is I'm trying to find out what is the best fit function. Okay. So this is in many cases I can fit the data with this kind of a function. Then I will train the estimated temperature, transition temperature is this, as per this fit. I can find a better fitting function which has a finite temperature divergence. Then as per that fitting function, I will have another estimate of the critical temperature. That's all we do. So right now, algorithms allow us to somehow go to these lower temperatures and reach these temperatures. Okay? Then we can again test whether this is making sense or not. But yeah, it's even in numerical simulations, we are far away from this.
But in the case of numerical simulation in spin-glass system, people generally use the Edward order parameter, Sherrington order parameter, even the Parisi order parameter.
Yeah.
So,
people have tried this also in structural classes. I mean, it's not. And so the overlap is very messy in the sense because you have to define a distance over which, I mean, what is the definition of in the case of spin systems, it's very clear that up, down, whatever, some time. So there is some structure you are looking at overlap of that. But here you have to
not as this.
right. So the overlap is defined over some distance a, for example. I mean, some particle has moved beyond this distance, you say no overlap. So overlap is always has this weakness of defining the cutoff. So that makes life slightly.
So, what is the state of art of this order parameter in spin-glass system?
A similar system actually we still use this kind of
Edward Anderson order.
So in our case, yeah, we still don't know. And people try to use this. So recently, I mean, if you just want to look at one attempt is basically looking at structural motifs. So I can say that some, let's say, local symmetry I can look at, like some, let's say what they call icosahedron and so on. Some kind of some particles are organized in the form of an icosahedron. Let's say that is the pattern that people see. Then I can look for icosahedral order inside the system and see if this is growing as I go to lower and lower temperatures. So that is one way. Or I can So in most structural measures that we have, these are all two-point correlations. So basically, I am asking if my particle is sitting here, what is the probability of finding another particle? But now I can take higher order correlations. I can take four body correlations, three body correlations, and yeah, people are trying on different things. So the problem is that the following: in some model, you can say that this order parameter is increasing. But this order parameter with a generic order parameter, you have to try it for different models and show that this is indeed the order parameter that is generic to this kind of behavior. It may not be the fixed, I mean, it could be very peculiar to that model.
And not only this, you have to also study the second moment of the order parameter that should diverge at the glass condition interface. So that should be supported by. Okay, so if there is no question, let us thank the speaker for an exciting.